Okay, thank you very much. I would like to thank the organizers for inviting me. It's a pleasure to be here. And in fact, the first time I give a talk for the dispersive people, let's say, because this is not really my area. Okay, so I feel a little bit also uncomfortable to give a talk in front of the experts. So what I will try to do is I will try to summarize somehow the work we've been doing with Yvan Martel and Claudio Munoz for the last more or less 10 years. I will start with the first step of this project, and then I will skip all the intermediate steps, and I will talk about the last result that we have, which is maybe the most connected with the first result. And I will also try to explain a little bit the method, which I think is somewhat different in the flavor than at least what I have seen so far, and what people here probably are mostly used to. Okay, so what I'm interested in are, in general, what I call scalar field models. So these are nonlinear wave equations in just one dimension. And they have a very simple form. So I will make just one picture if there is of a typical potential W. Okay, so in my picture, it's not very symmetric, so I'll just make it more symmetric. Okay, that's very easy. But in general, it doesn't have to be symmetric. And in fact, we worked on cases with no symmetric potentials. But because I will talk about odd kinks, I will assume that the potential is even. It has two wells. You can, but in general, it doesn't have to have two wells. But what I'm interested in are always only two wells, two neighboring wells. So this potential may have infinitely many wells. I will give examples in a second. And what can be said in general about this problem? Of course, that there is the energy that is conserved and the momentum that's conserved. And in general, there are no other conserved quantities, although for some special cases, there are many conserved quantities. All right, so, and I will always write it as a system. It's more convenient. So what are the examples? So the famous example is, of course, the sine-Gordon equation, okay, where the nonlinearity is just sine of phi. And the potential, you can take it 1 minus cosine phi. It has infinitely many wells. It's periodic. And the second, I think, most interesting example is the phi4 model. The phi4 model has a very simple cubic, quartic potential. That's why it's called phi4. And the nonlinearity is cubic. It's very simple. And then, in fact, these two equations, or two models, can be embedded in what is called phi2 hierarchy. So what you do is, in this hierarchy, what you have is a truncation of an infinite product that approximates 1 minus cosine phi, or with a shift or no shift. And you choose lambda n and this mu appropriately so that these products converge as n goes to infinity to the sine-Gordon model. But of course, when you start with the truncation, let's say at 1 of this potential, then you get phi4, and then the next in the hierarchy will be phi6, and then phi8, phi12, and so on. Okay, so you have the whole hierarchy of models, and the people also worked on, and we also worked on those models, the phi10 and phi12, and so on and so forth. Okay, so what are the interesting objects for me? Of course, you have to decide on what you want to do with this kind of thing. But what is the most interesting object for me is what is called the kink. So all these models have kinks, and kinks are heteroclinic orbits that connect to neighboring wells. So in the phase plane, you have this heteroclinics. And of course, this is a whole family. So because you can shift, you can translate, and you can take minus heteroclinic. So I will fix typically in the phi4 case, the heteroclinic, I'll choose the one that is increasing and it's odd, tangent hyperbolic. And they're explicit for the phi4, they're explicit for sine Gordon, and there are some other models for which they're explicit. Okay, for instance, for phi6, kink is also explicit, but it's not symmetric, so it's a different case. It's a kind of separate case. Okay. But then there are other special solutions that are known only for the sine Gordon equation. So one of them, and I think it's the one that is most puzzling, is called the breather. So this is a solution that is localized in space. So there should be x here. So this is a small typo. So this is x. And so it's cosine hyperbolic of ax and cosine bt. So this solution is localized in space. So if a is small, you can think of it as simply cosine bt divided by cosine hyperbolic ax. And it's periodic in time. And these parameters a and b are related. A squared plus b squared is equal to 1. And you can, in some sense, you can make a superposition. So when I say superposition, it's not exactly superposition. You can refer to it as Backlund transformation kind of construction or something like this. But in certain limit, it looks like a superposition. In fact, if the limit of the amplitude A is the amplitude is small, then it looks in the limit like a superposition. This solution is called wobbling kink. It's a super solution of kink and a breather. So this is a solution that looks like a kink, but it's a kink that wobbles periodically in time. Okay. So these are interesting solutions and interesting objects. And as I said, the only case where they are known for the last two, they are known as the sine Gordon equation. And the sine Gordon equation, as I said, well, I didn't say that, but everyone knows that the sine Gordon equation is a completely integrable system. It has infinitely many conservation laws and so on and so forth. Lax par. Okay, so what I'm interested in is to study this kind of models in the energy space. So the energy, as I said, is this. It's the conserved quantity. And what I want to consider are initial data of the form, the kink plus something small. And the small perturbation of the kink, it should be bounded in the energy norm. Okay, so this is what I call the energy norm. So what is known, it's not very difficult, in fact, to prove that for all these models, there is a global solution with finite energy, okay, of this equation. So this is not maybe a big deal. But what is known also that the kinks are stable, okay? So if you start with the initial data that has a small energy norm, then the perturbation will stay small in the energy norm forever, okay? And this is an old result by Henry, Perez, and Brzezinski from the 80s. So the question that I'm interested in is the kink, this kink, okay, H0, of the phi4 model asymptotically stable in the energy space. Okay, that's the question, and this is the question I I asked someone, I asked my postdoc, in fact, about 15 maybe years ago or something like this. And at the time, I was sure that this is something done, okay, that everyone knows it's just a matter of finding the right paper. Then I found out that there is no paper. In fact, my postdoc said that there is no paper. And this is how I got interested in this question. And of course, when I asked this question to myself, I didn't even know at the time Ivan or Claudio, I was very stupid, because one thing that question is not not correctly stated, because it asks about stability in the energy space, but that cannot possibly be proven, okay? Because if the energy is conserved, so this is not the right topology to look for the asymptotic stability. And the second thing is that there is Lorentz invariance. So as soon as you add a perturbation to the kink, it will start moving, and it will change also its profile according to the Lorentz boost. And so the only way you can you have to modify this question in two ways. Once, you have to restrict the class of perturbations so that somehow you get rid of the Lorentz invariance. And second of all, you have to change the topology, okay? So the initial data can be in the energy space, but the asymptotic stability cannot be proven in that space. There has to be other space. So perhaps the most interesting for physicists, I think, would be that the small perturbations should go to zero as time goes to infinity in L infinity norm, okay? But this seems even now it seems to be a very hard problem. I'll go back to this at the end of this talk, okay? So one possible weakening of the statement would be to relax a little bit and to say, well, I don't want L infinity to be taken in the whole space. I want L infinity norm to be taken in a compact interval, maybe any compact interval, but still compact interval. And this, in fact, is very close to the topology we work with. So what we use is the local energy space. So this is the energy norm over a compact interval I, okay, or a compact set. Now this is not still completely correct in a sense, because what we work with is a weighted version of this norm, but this is maybe too complicated to state with the weight. So it's much simpler just to say compact set. These things are almost equivalent. Okay. Right. So what you can do is you can write the phi4 model as equation just for the perturbation. So this is very simple, and I write this explicitly because it's important, or it was important that it was explicit. So in particular, you have a very explicit linear part, and this I also get a little bit ahead of myself. But this explicit potential here, the sign squared, that's known as Porsche-Teller potential. And for this problem, you can write the spectrum completely. Okay, so this helps a lot. And so what we proved with Claudio and Ivan in 2015 is the following: if you take the initial data in the energy norm sufficiently small, and it is odd, okay, odd in space, then it is asymptotically stable in the local energy norm, okay? So that for any finite time interval, this norm goes to zero. So what is the meaning of the oddness? The oddness is important because it eliminates Lorentz invariance. So if you add, because you have oddness is preserved by the equation. So if you have odd initial data and the kink is odd, everything is odd and you cannot move. Okay, so this helps. Okay, and so let me explain a little bit what are the steps or what the proof consists of. In fact, the first step, and this is something that we learned from the paper of Sofer and Weinstein in 99 or 2000. So this is a very famous paper in Invenciones, where they worked on a problem in 3 dimensions. So this is a Klein-Gordon equation in 3 dimensions with the potential. And the potential, of course, is to eliminate Lorentz invariance, to eliminate translations, and so on. So just like in our case. And they prove asymptotic stability of zero solution, zero solution, in fact, to their problem. I don't want to speak about this problem because this is not the subject. But anyway, what they introduced is the spectral decomposition. So what they introduced is they noticed that in order to understand their problem, for their problem, the potential had just one eigenfunction, okay, is that you have to decompose the solution. So we do the same thing. We decompose the solution into what is called the internal mode. So this is y1 is the second eigenvalue of the linearized operator, okay? That is in fact this eigenfunction. This eigenfunction and the eigenvalue are explicit, as I said, plus a perturbation which is orthogonal to the internal mode, okay? So this is called the internal mode. So you make a convenient decomposition of the perturbation into the internal mode part and the rest that is orthogonal. And then what you want to do is you want to write the equation of the system for z1 and z2, and just a function of time, functions of time, and for the rest, for the perturbation. That's what you want to do. Okay. So this is. It turns out this is not the most convenient way to think about it. The more convenient way to think about it is to think of variables alpha and beta. So what are alpha and beta? In fact, alpha is the real part. If you think of z1 as the real part of a complex number and z2 as the imaginary part, so alpha is the real part of the square of this complex number, and beta is the imaginary part of the square. So, well, somehow you can always do it with the Hamiltonian system. As you see, the z1 and z2, or alpha and beta, they solve basically Hamiltonian. They satisfy basically Hamiltonian system. Okay. So when you do this little modification and you project and calculate, you get a system for alpha and beta. So in this system, dots are just terms that are nonlinear and may be very complicated, but to me they are somehow controllable. Okay. So I only fix the linear part plus some nonlinear term that couples these 2 equations. So there is a little detail here with that alpha and beta that are squares do not appear in the second equation. The second equation, you have z1 square, but you can fix it, okay? This is very easy to fix it by changing again variables. And strictly speaking, it's not even necessary, but this is more everything becomes more transparent when you do this. So when you do this, you see you have for the alpha and beta for the finite dimensional part, let's say, you have a Hamiltonian system, okay? And for W, for the perturbation expressed in these new variables, you have also a system, but the point is that their important parts are just linear, and they are linearly coupled, okay? They're linearly coupled. And there is also an important feature or aspect of this problem. What is this function f, okay? It turns out to be something important, this function f. The coupling function, okay? It has to satisfy certain conditions. So what we actually prove is the following. We prove that the integral of z to power 4 and the integral of the perturbation, infinite dimensional perturbation squared in time, they're finite, okay? So this is a little bit more than to say that just these two go to zero, okay? So this is a little bit more. And somehow we give, some very maybe weak form, but we give some rates. And the rates are different. This is power 4, and this is power 2. And this, in fact, is already known from the Sofer and Weinstein. Okay, Sofer and Weinstein, they also have this, and even they mentioned it in the title of their paper. Okay, it's unusually slow decay or something like this. I forget exactly the formulation they have for this. Okay, so the internal mode, basically, it's expected to decay slower than the rest. Okay, and then numerically, we computed for a different model for sine Gordon on a wormhole with Piotr and Dunajski, Kal, the rates of decay for the analogous problem, and the rate of decay is T2 minus 1/2. So this is kind of consistent with the Z to power 4, okay? And if there is no internal mode, then the decay is like T2 minus 1/2 in L infinity with a logarithmic phase correction. And this is done by Luhrmann and Schlag, for instance, in the case of sine Gordon equation and with odd perturbations. Okay, so let me continue with the proof. The proof consists of calculating derivatives of two functionals. Okay, I call them virial functional. So first virial functional is for the infinite dimensional part, and second virial functional combines the finite dimensional and infinite dimensional part. So it's not so difficult to understand what is the first virial. This is the momentum, okay, and you add to it a correction that I will explain where it comes from. The correction is to eliminate some not convenient term, okay? So this is not so difficult to understand. Well, this one is more complicated. It's a kind of ad hoc functional that we invented, but it has some logic, okay? You have a Hamiltonian system, and you combine alpha with W2 and beta with W1, okay? So somehow you can understand there is a kind of structure here, okay? So what happens when you take derivatives of this? So initially, because you know stability, these two functionals are controlled, okay, initially. If you take derivatives, you get something, okay? You get somehow bilinear form. This bilinear form, let's say that you can show it's coercive. Okay, if you can show that this is coercive, you integrate, and then you're done. Okay, so that's all there is to it. So the main trouble is in fact to show that the resulting bilinear form is coercive. This is the whole problem. Okay, and what we did in the first paper, we used Maple to calculate some constants and basically some constants of some integrals in order to make sure that this bilinear form is coercive. Okay, and in this bilinear form, or in these functionals, there are two functions that have to be chosen. One is phi, and this phi, I will tell you how it should be chosen in a second. And the other one is g, and I also will tell you how it should be chosen. But what we did in the first paper is that we choose this g not completely correctly. This, now, as I think, as the way we think about it, okay? It was an ad hoc choice that complicated the bilinear form and made it, well, somehow necessary to use this computer thing, okay? So let me explain this. So let me explain this virial calculation. So the virial calculation is very simple. So you start with the system, okay, as I said, and the linearized operator is not so important what it is, just a Schrödinger operator. And let's say that your function, your weight is x. This is not correct. It cannot be x because in general, in the energy norm, this functional would not be bounded, okay? But let's say it is correct, okay? Let's say we can put x. You take the derivative in time of this. So when the derivative falls on W1, then everything by integration by parts goes away, because W1, derivative of W1 is W2. So, okay, and that's the reason why there is this extra term added. It's in order to eliminate W2 to begin with, okay? And then you calculate when the derivative falls on W2, the derivative falls on W2, you just do integration by parts, and you get bilinear form in W1, okay? And if you are lucky, then this new potential xp prime is negative, and then you get something that is at the end, when you change sign to minus, you get something that is non-negative, and you can integrate. But in fact, you are not lucky. You're never lucky. Okay? This never is. It has the right sign. Okay, this is what happens. Almost. Okay, so the second functional is also very simple to calculate. And again, there is a cancellation. When the derivative falls in alpha prime and in alpha and W1, everything goes away, essentially. You get just dots. The interesting thing is when the derivative falls on W2 and on beta, and you do the calculation. So you calculate what it is. And then you use the equation, and this is, in this equation, you remember there was a coupling term, F, that couples the W equation and alpha beta equation. So this coupling term appears here, and here you have an extra alpha term with W1. You combine them, you integrate by parts, so you get something for G. You get an operator operating now on G. And you get alpha squared, okay, times Fg. And again, if it so happens that this term goes away, you get something quadratic, and you can integrate, and you're done. Okay. So what you want to do is you want to disappear, let's say, the mixed term. Okay. So in order to do this, you have to choose G. So the best choice of G is to choose G to be the generalized eigenfunction of the operator L with the eigenvalue 4 mu squared, okay? But let's say you do this and you are unlucky and F times G is 0, so this goes away. So you don't want that. So F times G cannot be 0, and this is what is called the Fermi-Golden rule. The Fermi-Golden rule tells you that this coupling term F multiplied by the generalized eigenfunction of this operator with this particular generalized eigenvalue, the product of these two is not 0. Okay? So if you, now this is not completely correct. You cannot choose G to be generalized eigenfunction of this operator, because such G is just bounded. And then this is not bounded integral if W1 and W2 are in the energy space. But there are ways to fix it, okay? So essentially you cut off and you do something and fix it. Okay, so now I will speak about the new approach, and this, as I said at the beginning, it took us many years to develop. In fact, in between, we wrote some papers on nonlinear Klein-Gordon equation, also scalar field models. But I will skip them and I will just go to the end of the story. So what I will consider is, again, this wave equation. And I will assume that W is an even non-negative potential. It's double well with wells at plus and minus 1. But if it's multiple wells and you are interested in two neighboring wells, what you can do is, if there is a symmetry, you can shift them to 0, and you can rescale time and space and the variables, and you can always get them to be at minus 1 and plus 1. So this is not a problem. It's not a real restriction, okay? What is important is the non-degeneracy. I didn't mention this at the beginning, but this is a very, very important condition. Without this condition, the things become complicated, more complicated. Okay? So again, for this kind of problem, there is a stationary solution. There is a kink, which is now not explicit, but that's okay. And I'm interested in studying this this problem for the perturbation U1, U2. Again, in the energy space, and I want to show asymptotic stability in the local energy norm. Okay, so this is basically the same problem as before, but I don't restrict myself just to the phi4 problem. Okay. So let me tell you what are the hypotheses. So the hypotheses are the following. So there are general hypotheses. So the linearized operator always has 0 eigenvalue, and the eigenfunction is h prime. Okay, and I will assume that it has just one odd eigenfunction y that corresponds to the internal mode. Okay, with an eigenvalue that is between 0 and the bottom of the continuous spectrum, which happens to be omega squared. That's the value of w, of second derivative of w at plus and minus 1. In fact, what is allowed is that this operator has another eigenfunction between between lambda squared and the bottom of the continuous spectrum. Just one eigenfunction, because this one eigenfunction will be even again, and it doesn't bother the odd perturbations. So this is allowed. The second condition is what I mentioned, the Fermi-Golden rule. So stated explicitly, the Fermi-Golden rule is the following. I take the generalized eigenfunction of the operator L, of the linearized operator, with this eigenvalue, 4 lambda squared. And what I want is that this object is not equal to 0. Okay? So this is F. This is what is the coupling between the alpha beta equation or system and the W system. Okay? And this is this name Fermi-Golden rule comes from the paper of Siegel from the 90s. And in fact, this is a kind of nonlinear version of the Fermi-Golden rule that is known in spectral theory and quantum mechanics. You can find in the book of Reed and Simon, I think in the 4th volume. Okay. So the new element is in this whole analysis is the Darboux factorization of the linearized operator. So the Darboux factorization, I think, well, of course, it comes from Darboux, but in the context that is close to ours, it appears in the paper, the famous paper of Dave and Trubowitz. And in fact, we learned it from the paper of Chang, Gustafsson, Nakanishi, and Tsai. And we also used it, the first time we used it was for the nonlinear Klein-Gordon equation. Okay, so what is this Darboux factorization? So you define two operators, U0 and U0 star. U0 star is just a joint of U0. It's nothing special. And they are based on the first eigenfunction of the linearized operator L, okay? And you directly calculate that L factorizes. It is U0 multiplied by U0 conjugate. Okay, so this is interesting, but what is really interesting is when you switch U0 with U star, and when you switch U0 with U star, you get another operator, call it L1. This is also Schrödinger operator, which has fairly explicit potential, and there is the L1 and U0. U0 somehow commutes, but not with L, but with L and then L1. So if I take L1 of U0, this is the same as U0 of L. And from this, it follows, it's very easy, that L1 has a principal eigenfunction, but now the principal eigenfunction of L1 is U0 applied to the second eigenfunction of L. Okay? So L1 has one eigenfunction less than L. So this is the nice and this is the key somehow observation, and this is the nice property of L1. So what you do is now you can repeat the same construction, but now you use the principal eigenfunction of the operator L1 to factorize not exactly L1, but L1 minus lambda squared. That again factorizes. And then what you do is you switch U1 star with U1 to get a new operator, L2, which is again a Schrödinger operator with a potential. And now this operator will have one eigenfunction less. So if the original operator had just two eigenfunctions, this new operator will have no eigenfunctions anymore. Okay? So this is the factorization. So now what I will so let me explain the third hypothesis. So the third hypothesis has to do with this operator L2. So what we assume is that L2 is such that this operator, so P2 is the potential of the Schrödinger operator L2, but in this Schrödinger operator, the potential is xp2 prime. And this xp2 prime comes from the virial calculation. And as I said some time ago, if you are lucky, this potential has a sign. Now you can somehow hope to be lucky, in fact, and to have sign of this potential, sign that makes this operator such that it is coercive, or it has not more than one negative eigenvalue. Lambda squared is the second eigenvalue. So the first eigenvalue is 0, lambda squared is the second eigenvalue. Okay. All right. So the result that we proved with Ivan is that if you have these three hypotheses, so there's the spectral hypothesis, the Fermi-Golden rule, and the hypothesis about the transformed potential, then the kink is asymptotically stable in the local energy space under odd perturbations. Okay, so now first of all, okay, so this is the result, and this is a general result in the sense that the potential now is not restricted to be phi4. But that's the difference. Okay. So what are the examples? So the example is the phi4 model. So for the phi4 model, you have explicit potential. You can calculate everything. The spectrum is known because of the Posch-Teller potential. The Fermi-Golden rule can be checked directly, and that was done by Delort and Masmoudi in their paper or book. You use just complex analysis. We originally just checked it numerically, but it's very, very straightforward to check it directly. And the P2 potential is 2. And so the last hypothesis of the theorem is trivially checked. Okay, so there is no problem. Now, what you can consider is another, so you ask if this whole method applies to some other problem, because if it just applies to phi4, then maybe it's not so interesting. But we took, so let me just say that in general, it's not so easy to check the hypothesis, of course, because neither the spectrum is maybe explicit, the Fermi-Golden rule is maybe not so explicit either, and the real difficulty is in the third hypothesis. We tried for several, or for some problems, which seem to be explicit, at least as far as the two hypotheses are concerned, but the third hypothesis is not so easy to verify, okay? Maybe you can do it numerically or something, but we didn't want to do it. But if you can look at this problem from another point of view, and you notice that these three hypotheses are robust. That means that if you perturb slightly So in this problem, if you know asymptotic stability of the odd kink for one problem and you perturb it in certain sense slightly, then you will also know asymptotic stability for this new problem. And this is because now the hypotheses, you don't check them explicitly numerically for some specific problem, but they are robust hypotheses. So we did it with the phi8 model. The phi8 model, you can think of it, so phi8 model is this, the potential is 8th order potential. And if you scale it properly, you have phi4 potential multiplied by some other term, okay? And it has 4 wells, plus and minus 1 and plus and minus m. And what we are interested in is the regime where m goes to infinity. This makes basically the potential like a phi4 between minus 1 and 1, okay? So let me explain this. So what you do is you rescale time and space, and you have the phi4 potential multiplied by something else. And you see that when m goes to infinity, this whole thing goes, let's say uniformly on compacts, goes to 0. So you just get 1, so you get phi4 potential. And then as m is very large, the phi8 potential can be seen as a perturbation of phi4, and then the hypotheses can be checked. Okay, they are robust; they can be checked directly, and you can prove asymptotic stability also in this case. So I still have a few minutes, so let me explain a little bit just the idea of the proof. So the same idea as before, you decompose the problem into finite dimensional and infinite dimensional. And there are 3 steps in the proof, okay? So first step is you use the first virial estimate just to control the derivative in some weighted norm, the derivative of the solution, in terms of the rest. So L2 norm of the solution and alpha squared. Then use the second virial estimate and the Fermi golden rule to control alpha squared in terms of the H1 norm, local or weighted. That's why I put W, because it's a weighted norm of H1 norm weighted, okay? So now you see that you have to close this. So you have to find a way to control W1x in L2. So in order to do this, you define a new operator, and this new operator is you apply the Darboux factor U0 and the Darboux factor U1, okay, to W. And then if you stay with this, you lose, because this operator are first order operators. So you lose 2 derivatives. So you have to regularize. So there is a little bit of this technical things. I call this regularizing operator X epsilon. So you have a new operator S epsilon W, and you write the equation for S epsilon W. So the equation for S epsilon W is essentially the same equation as before, except that now the operator is L2. And I told you that L2 is a better operator than L, because you have a chance to have coercivity with this operator. And there are other terms. There's a commutator, and there are many other terms that you have to control. And notice that the equation for V contains W in particular. So you have to know how to control W in terms of V, and also V in terms of W. Okay, so you have to do this. So the main, in fact, control is how to control W in terms of V. Okay, this is V, and this is how to control W in terms of this operator. This we call coercive estimate, and this is where you use the orthogonality condition. This is where you use the oddness. And once you have this, you can use the first virial estimate again to control the derivative of V. That allows you to control the derivative of W, okay? And then you can close all the estimates, and you're done. Okay, so this is in a nutshell the scheme of the proof. So let me finally tell you about the state of the art. So I said that this is not exhaustive state of the art. Why it is not exhaustive? Because I will only tell you about the problems that have to do with the scalar field models, but people worked on the nonlinear Klein-Gordon equation and also nonlinear Schrödinger equation. And there are results that are somehow brothers, okay, or sisters to this in this other context, okay? So, but that would be too long maybe to mention all of this. So the first, maybe this is one of the most recent results, is by Luhrmann and Schlag. That is, they proved asymptotic stability of the sine-Gordon kink under odd perturbations. So this you have to explain a little. Also, I have to explain this a little bit. So, of course, you cannot prove asymptotic stability of the sine-Gordon kink under odd perturbations because you have wobbling kinks, okay? But they worked in the weighted space where wobbling kinks do not appear. They are big perturbations in the suitable weighted space. Wobbling kinks are big perturbations of the kink. They do not appear, and this is a very interesting paper. They use a very special property of the sine-Gordon equation of the potential of the potential of the quadratic term that you get when you linearize around the kink. So this is very, very interesting. Another interesting contribution is by Alejo, Munoz, and Palacios. They construct a manifold of initial data for which the sine-Gordon kink is stable. And this manifold does not consist of odd initial data. So this is a different type of initial condition, okay? But this is just a manifold of infinite codimension. Now for the same sine-Gordon equation, Chen, Liu, and Lu, they use the integrability structure of the sine-Gordon equation, and they prove the soliton resolution for this problem, okay? Also in weighted spaces, so it's not at the energy space. And there are many related, or several related works to this by Lindblad, Luhrmann, and Sofer, by Lindblad, Luhrmann, Schlag, and Sofer. And they work with the Klein-Gordon equation with quadratic and cubic nonlinearities. So this you can think of a model. One way of thinking about this, okay, in fact. So this would be a model of the operator that you obtain, nonlinear operator that you obtain after you linearize around the sine-Gordon kink, or around the kink for phi4 or for any other of these models, okay? So they prove asymptotic stability also in weighted space, and they give rates in L infinity norm, and they give quite a detailed description, okay, of what is going on depending on the properties of the nonlinearity. Okay, now Kukania, Maeda, and Skrobonia, they did sort of generalization of the theorem, the second theorem I mentioned, and they allow for more than one internal mode. Now the Lord and Masmoudi, and this is something I mentioned, they tried to obtain L infinity bound for the odd perturbations for the kink. But what they obtained finally was an asymptotic, but for the phi4 model, but for finite time. So for finite time, they can get a rate of decay, okay? And the time depends on the size of the initial data. And that seems to be very difficult problem to overcome, okay? And finally, I should also mention the work of Germain and Pusateri, where they used the distorted Fourier transform approach to prove asymptotic stability of kinks, but with no internal mode. So they also have to assume oddness. They don't allow for Lorentz transformation, and there are no internal modes. Okay, so this is all I wanted to say. Thank you very much.